Okay, this is Jack Jackson back again, and we're continuing our exploration of the side angle side property. We looked at it last video for Euclidean geometry, and we found out that the side angle side condition was enough to make two triangles congruent in Euclidean geometry. Well, what about in hyperbolic geometry? So just like I had these applications here, side angle side exploration in Euclidean, I also have the same thing for hyperbolic. So first of all, let's just review real fast. Here's what a hyperbolic triangle looks like. Here's the hyperbolic half-plane edge. We're using the half-plane model, and so we have this up here. Let me just open that in the app. Gives you access to hyperbolic tools up here, and we can see this is our triangle here. This is what it looks like, and these are the measures of the sides measuring with the hyperbolic distance metric, lengths of the sides, and these are the measures of the angles. Okay. Now, let's take a look at the side angle side exploration. It works just like the one in Euclidean geometry that we looked at in the last video. So once again, you can have a side, an angle, and a side specified. We start with a free point, free to move anywhere in the hyperbolic half plane, which is up here. We can't put it on the edge or down here. Those points are not in the geometry. So we've got a point up here. We pick a circle centered at that point of whatever radius that side one. Okay, and it's staying the same radius here. In hyperbolic geometry, the lengths or distances are compressed down here toward the edge and spread out further up. So the center of this circle is a little bit lower. It is a Euclidean circle, but the center is lower here. And the hyperbolic distance, which is the length of that radial line segment, is the same. It's 1.2 specified by this slider or box here. All right, so anyway, we have that. Next, we make the angle, just like we did before. Make an angle. There's also one down here, but let's make the one up here. And then we go out a circle centered at A of this size B, which about 1.35 units now. And notice it only touches that ray one time, and so that has to be C. There's our final thing there. Okay. Just like in the Euclidean one, there is another one down here where we could have rotated the angle down here. But if you do it, it may look different to us as Euclidean objects, but as hyperbolic objects, they are actually congruent to each other. So once again, we get really the same conclusion. You can always go out any distance, any positive distance. You can always go out any proper angle measurement. You can always go out a proper distance, and it will always touch that ray one time. And so that's going to finish it off. And it doesn't matter whether that's what kind of angle we're looking at here or what kind of distances. Some of these tools are a little tricky here in the hyperbolic, but at least there shouldn't be any place where these things break where it's not possible. So once again, side angle side, always if we give a side angle side measurement condition where we're given a measurement for side, a measurement for angle, and a measurement for the other side like this, where the angle is included between the two sides. See, look here, the angle is here, and the two sides are right next to it. Two angles are right next to it on both ends. Okay, and so that condition will always give us one congruence class. Or if we have two triangles, this time we don't care what the measurements are, but just that we have a side, angle, and side in congruent corresponding pairs, then the two triangles have to be congruent. So in this respect, hyperbolic geometry works exactly like Euclidean geometry for this condition. Interesting. Let's try out the other geometries in the next video.